for diagnosis classifications. 6 algorithms were chosen and compared to decision tree, random forest, multinomial naive Bayes, k-nearest neighbor, support vector machine, and multi-layer perceptron classifier, which uses the backpropagation algorithm. These selected algorithms were evaluated on a dataset containing 686 records. In order to obtain the dataset, data cleaning was performed. The dataset originally had around 4,000 records, but after removing the duplicates, only 300 remained. And given the small amount of data that remained, new data would be needed in order to train the algorithms. So therefore, using a large number of publication and reports from PubMed, new symptoms combination were added to the dataset, resulting in 132 symptoms and 41 diagnosis classes. In order to showcase how the diagnosis classification could be integrated for a medical platform, a web application was developed. The application allows the user to get diagnosis based on the symptoms, and he also has the possibility to choose one of the 6 algorithms to be used for the classification in order to receive the 3 most likely diagnoses. To illustrate that the diagnosis can be provided by doctors online. A chatbot functionality is used to ask doctor-like questions. For this chatbot, the dialog flow framework is used and customized, and the chatbot is trained with our symptoms and diagnosis in order to understand the user's concern and provide useful information. In order for the algorithms to achieve the best performance, parameter optimization is performed to improve the models. The optimization was based on several tests and analysis methods used to analyze the model's performance. And for this analysis, the training set size represents 80% from the data set and the test size 20%. Additionally, also the 10-fold cross-validation method was used, where the data is split into 10 folders, and the method trains the model until all the folders are both used as testing and for training. And for each step, 9 folders are used for training and 1 folder used for testing. One of the methods that was used was also grid search CV. This method receives all the possible values for the parameters and performs parameter value combination for all and trains the model, and then gives us scores for each of these combination. And this method was used for the support vector machine algorithm to determine the best values for C, gamma, and the kernel parameter. The parameter grid contains the following values, and in this case, the chosen values, the best score was obtained for C equal 10, gamma 0.1, and kernel RBF. During the algorithm analysis, also the 10-fold cross-validation was used to get a more realistic value for the accuracy. Here, the gamma parameter indicates how many samples are considered when making the prediction. If the gamma is large, that means that only points that are very close are considered, described also as near range. And if the gamma is small, then it's a wide range and the model will have a more generalized solution. And for the C parameter represents how strict the model is when misclassification occurs. The larger the C value is, the stricter the model becomes. But too large values for C could also lead to overfitting, and too small values for C would mean that the model is looser and therefore many misclassifications occur and also a smaller accuracy. And with both approaches, it can be observed that for C10 and gamma 0.1, the best accuracy is received, and for larger values for gamma, the accuracy even starts to decrease. And for the decision tree, the analyzed parameter is alpha, which represents the cost complexity parameter, indicating how much the tree is pruned. By default, this parameter is 0. For this analysis, it can be seen that for gamma between 0.003 and 0.009, the best accuracy is achieved around 68%. For the random forest classifier, the parameter for number of estimators is optimized, and as seen in the graph, the accuracy steeply increases from 0 to about 20, and then it stabilizes and remains around 95, 90, 94%, meaning that the value of 30 estimators would result in a good performance. For the multi-layer perceptron classifier that uses the backpropagation algorithm, the number of hidden layers and the number of epochs is analyzed, and the accuracy for the model reaches a maximum of 94% when the number of hidden layers is above 20, and a similar accuracy is also received when training the model for more than 10 epochs. Also, a comparison before and after optimization is presented in the following pictures. It can be clearly seen that the accuracy for all of the algorithms improves. And for naive-based support vector machines, multi-layer perceptron, and random forest, even achieving an accuracy around 90, 95, 93%. But the only algorithm where there is no visible change is the decision tree, because um, for this algorithm only the pruning parameter was optimized and not many nodes were pruned. Therefore, there was not a big improvement on the accuracy value. Another way to observe the improvement after the optimization is with the help of a confusion matrix. The values that are not on the main diagonal represent the misclassifications, and as in there are a lot of wrong classifications here, and after the optimization only two remain. And this type of visualization gives us also insight into which diagnoses are usually misclassified, or for which diagnoses more training data would be needed. Now I will present a short demo of the application. The application has the diagnosis classification functionality and chatbot, and also a feedback loop in order to improve the model and achieve a better classification result. For the diagnosis, here we can give the input symptoms. Um, These are the 132 symptoms that are also in our data set, and here we can choose one of the algorithms with naive Bayes, and here we get the three most likely diagnoses and their confidence level. And this can be done for all the algorithms, but if we add more symptoms that don't contradict each other and that are related to each other, we will see that the confidence for the algorithm increases. And we can see now that for all the algorithms, the predicted diagnosis is hepatitis E. And if we think that this is not a correct classification, we can always give feedback and provide the correct diagnosis. Let's say hepatitis D, and then we will receive a confirmation that our feedback was received. And to showcase that this could be done with the help of a virtual doctor, a similar approach is presented with the chatbot. We type in our concerns and we will get a response. We will have to also to give our symptoms. And we can also give more symptoms at a time. And now the algorithms will return us the prediction, which is pneumonia. And if we think that this is correct, we say yes or no, and we will give the correct correct diagnosis. I have only the conclusions left. And for the feedback, the algorithms are retained after a certain amount of received feedback, and the prediction will become more accurate over the time. And for the conclusion, the research work could be further extended with new diagnosis classes. Also, more factors could be taken into account, like the severity of a symptom, the patient's age, the gender, the region when the patient comes from, and also a previous patient's diagnosis could be taken into consideration. And all these points will lead me to conclude that such an approach can be used on a platform to achieve a fast and accurate diagnosis classification. Thank you for your attention. If you have any questions.
Yes, I have a question.
Yes?
So, you mentioned that this is a very active research field.
Yes.
How, so probably a lot of researchers are doing research in this field.
Yes.
Does your work compare with what you noticed in the literature in general?
Yeah, I read a lot of research, and most of the papers that I read actually focus only on one particular diagnosis, and the classification is usually binomial. So if the diagnosis is present or not. So, but I didn't find any research where there are taken more diagnoses into account, and the classification is based on the symptoms.
Okay, thank you.
Thank you. Well, I think that this approach could be extended a lot more, and with a lot more diagnoses if the data set contains the training, and I think would result in very good performance if the all of the algorithms are combined, and maybe the most what the most of the algorithms predict, that is chosen as the value. I think that the algorithms could find patterns maybe that uh, the doctors even didn't notice, or because it focuses on such large amounts of data. The main problem that I had was that I didn't find much data, and because all the data is actually private, and I, I the data set that I have is not so big. But I think with very big data sets, this could be have a even better improvement and a better results.
I think we can then we can move on to the second presenter, Miss Ioana Keres, with a paper Artificial Intelligence Art for Public Ethics Debate. So
Yes, can you hear me?
please.
Can you see the presentation? Okay. So my work is about artificial intelligence art for public ethics debate. An overview of the presentation. I will start with an introduction, then I will talk about my concept, briefly show the related work and the implementation details, and in the end, the experiment and the results. How do people make decisions? When a person has to take a decision, he has to be presented a multitude of sources of information that show the different sides of the problem. Due to the COVID pandemic and the rapid growth of technology, a large percentage of people use social media as their main and only source of information. The information user receives is being filtered by artificial intelligence algorithms that rank each post based on like, comments, and time spent watching. But which are the downsides of this shift to social media as the main source of information? Because algorithms feed users only with desirable content, they create the effect of echo chamber. In this echo chamber, users see only their amplified beliefs, and this is why they are getting more and more separated from reality. Deepfake has become a popular technology which allows the creation of fake media on a targeted person. It has already started to be weaponized by creating deepfake pornography. The distortion of information also changes the opinion about self. Artificial intelligence algorithms remove imperfections, features that humans do use to display the perfect image. This is making people feel like everyone around has the perfect look and is the cause of increased dissatisfaction of people with their own body. The artificial intelligence advancement impacts society as a whole, not only the specialists who understand and develop these technologies. Our society needs a way of debating meaningful ethical problems on a large scale. I argue that the latest form of art created using AI technology are a solution to involve the population in the analysis of complex ethical issues. The concept behind my installation. My installation is made of a blue room, a screen, and a webcam. It is structured in three parts that match the exact parts of creating an online profile. Exploring the platform, accepting the terms and conditions, and having your own profile. The first part is inspired by Dante's Divine Comedy and is structured in three circles of hell. In order to explore the platform, the user has a skeleton alter ego. The true shape of the viewer starts to appear only when he projects ideas found there using his own body. The first circle of hell is limbo, where are the great philosophers and thinkers. But today people don't read books, they quote from Facebook or Instagram. So the first circle is filled with quotes that inspire some and terrify others, like the one used by ISIS in their recruitment campaign. The second circle of hell is lust, and it shows how extreme can we become in trying to achieve the beauty standards imposed by society. The third circle is anger. In the last period of time, anger and extreme violent reactions seem to spread like a disease. How much is the social media involved in the growth of this extreme organization? After the viewer experiences the platform, he has to sign the terms and conditions, which is the modern Faustian bargain. He allows the software to use his private data. The third part is exploring the profile. The viewer can see itself inside the screen like in a mirror. The body it has looks like its real body, but in fact is generated by a neural network. The user can control the alter ego from the mirror, but from time to time glitches appear. In these glitches, the program takes control and the person from the mirror becomes independent. The alter ego from the mirror can wave back to the subject, dance, or do anything random. There is a ping-ponging control over the image between the user and the computer in order to amplify the confusion between reality and fiction. Related work. In image-to-image translation is the main architecture for image generation. And in the artistic direction, we have Deep Dream Generator with programs that can dream, and the creative adversarial neural networks with stylistic approaches. The implementation. In the first two parts, the user is interacting with the platform. But in the third part, the user already sees on the screen a deepfake of his own body. Due to the complex capabilities needed, the system had to be distributed from a hardware perspective. The system has to be moved easily between art exhibitions and may work in diffusion environments like dust and moisture. On the other hand, it also has to have a high computing power to calculate the weights of the generator in less than 12 minutes. So it is split between the local component and the remote component. On the local component is at the user location. The location of the physical device is relevant for the quality of the images taken. Light 2 has to be 3 times stronger than light 1 in order for the user not to cast any shadow on the background, complicating the frame. And the frontal light allows the workframe to capture small details. From a software perspective, the local component has a scene decomposer, which takes the frames and decomposes it into skeleton, background, and person. Then, the scene composer takes all the partial images computed. It creates the frame that will be displayed on the screen. From the person image, a mask is computed that acts as a display area for the scene component, giving the illusion of projecting through the body. The part of the body that is not over any component is replaced by the skeleton, and the ring of head is added behind the visible components. It is also saving tuples of the person and its skeleton to train the neural network later. The remote software component is on another server in another location. It is designed for heavy computation and has the objective to train as fast as possible the generative adversarial neural network. The neural network is composed of a generator that has to compute realistic images of the body starting from the skeleton, and a discriminator that has to distinguish real from fake images in order to improve the overall system. Once the total neural network is computed, the weights of the generator are sent back to the local component, which is at the location of the installation. The final part of the local component is the third part, which generates the fake body. The system computes the skeleton from the current frame and then feeds it into the generator to generate the fake body. When the system becomes independent and the image from the mirror is moving independent, the system only alters the joint of the skeleton, then feeds forward inside the neural network and obtain a body in a different position than the user currently has. From an artistic perspective, the project is a unique combination of the latest technology with elements of classic European literature. Each circle has a different chromatic scheme that matches the information presented in order to amplify the psychological impact. The third part is focused on the psychological impact of deepfakes. In an online era of reduced empathy, the subject is becoming, for a short period of time, a victim of deepfakes in order to fully grasp the implication of this technology. Experiments and results. As we can see from this image, which is obtained during the time I trained the neural network, the system learns very quickly. Already from epoch 1, that means one iteration over all the data, we can see that the system learns how a general shape of a human looks like. From epoch 10, we can see shadows and the color of the skin, and in the 20th epoch, we see the texture of the skin, the texture of the clothes, and a clear distinction between them. To evaluate the results from something else that might view, I had to choose some metrics. So the first matrix is on the graph with orange, and is mean squared error. Mean squared error is calculating based on pixel-to-pixel subtraction. We can see in the graph that it is decreasing abruptly, meaning that on pixel-to-pixel differences, the images have a high quality. On the other hand, structure similarity index measures the similarity between two images. We can see that after 20 epochs, it is larger than 0.8, which is a very good result. This metric is more accurate for evaluating image generation because it evaluates the structure of the image as a whole. The conclusion.
Please.
The system presented is a complex artificial intelligence art installation that combines powerful technologies in order to give the viewers a meaningful experience. Its performance of creating deep take of the user body in under 12 minutes, along with the complex scene construction, make it appealing for the public. The project offers a new perspective on how to approach technology ethics on a large scale by involving people in the exploration of artificial intelligence. My work can be extended by artists in the audio and visual direction and by programmers to improve the neural network. Thank you for watching.
Thank you very much. Questions, please.
Yes,
Okay,
I have a question.
Yes, please.
So is this art installation actually installed somewhere physically where we can experience it?
Well, it was in my apartment and it was pretty complicated to make. So I do have the materials to install it, but right now it isn't exposed anywhere. So I am really struggling to find some art exhibition where I can expose it. I really believe in this idea and I think it could change, it could bring a new direction to art. So if you have any suggestion, I am more than happy to hear them. I would like to, but right now, no.
Okay, so where is the public ethics debate?
Well, so we have right now a problem in our society, and that problem is the lack of communication. So the echo chambers are an example of it. So how can we communicate in this era with the people? How can we talk about such an advanced technological concept like artificial intelligence with people, for example, who have a total different specialization? And my approach is to offer them an experience. So each person can experience artificial intelligence, different social problems that we have in our society and how technology affects us from his own perspective. Because this is what art does. It goes beyond words. It goes straight into feelings. And once a lot of people experience these feelings, they can talk about it. And each one can have his own vocabulary, his own way.
Okay, we agree on that. But where is the debate? Or where is the ethics?
Well, all the installation is based on ethics. For example, the first 3 circles of hell. Also, the concept of the Faustian bargain. How okay.
What do you mean by ethics?
By ethics, I mean what we should and should not do. What is good and what is bad behind some. I mean, without taking into consideration the legal part.
Okay. Other questions, please. So no more questions. So perhaps we can move on to the next.
Hello, can you hear me, see me? Okay. So I am Iaconu Bogdan Alexandru, as mentioned. My work has to do with some algorithms in artificial intelligence in Pokemon battles. Pokemon is a popular franchise. I think many of you have heard of Pokemon from some source. My focus is on the games that appear every year and they have some new content added to them. Pokemon games have many elements like storytelling, team building, exploration. But most notable is the Pokemon Battle, which is a turn-based game with simultaneous turn, where the opponent and the player have say the same turn to act, and they have been so popular that when the internet raised, some simulators that focus only on this aspect of the game, like team building and battling, have been rising up in popularity. Some online platforms also were made. My experiments were done on one of these platforms, Pokemon Showdown. And so, being a new game has some not meaningful research done on it, like chess has done, a lot of games on the classical sides has statistics and search research done on it. Pokemon, it's kind of new. It first appeared in '94, and I hope that this will bring some new light to the Pokemon battles. First, I will like to talk about the state of the game. Because it's a game, we need to find some sort of information during our turn. The most important one is the active Pokemon. You can see in this photo that we have 2 Pokemons on the field that can take more action than the ones on the back, the reserve Pokemons, which are there just to switch out our Pokemon when our Pokemon will reach 0 HP. And so faint. Some other information we have is known, and also it has some hidden information from the perspective of the player, the opponent. We can see in the opponent Pokemon's some details, but not all of them. We can see that the opponent Pokemon has 80% HP, let's say, but we don't know exactly their abilities. They say possible abilities, or we can see we can't see the statistics that it had. And one more thing, the weather and the site conditions are across the battlefield, so it affects both active Pokemons. I have chosen to represent my game in imperfect information game, as stated by Kevin Leighton Brown and Yoav Shoham. An imperfect information game in extensive form is a table G with, you can see, a lot of elements, where N is the set of players. So we have the agent and the opponent. A is the set of all possible action and switches that can happen. As of right now, all the moves are counted at 826 or so moves and 809 Pokemons. So we can do a lot, 1,600 actions possible, but not all of them in just one turn. H is the set of non-terminal choice nodes. We can see them as all non-leaves nodes in a tree. That is the set of terminal nodes, where it contains the states in which the Pokemons of one player all fainted, so all their HP is reduced to 0, and so the other player is declared the winner. And also we have the action function, which assigns some of the actions from A into one of the nodes. So we have the nodes, the leaves, and this action function states some more information about what can happen in a node. We have the player function, which assigns what players can do their action on some node, but our game has only 2 players all the time, and until the lift nodes, they can do both something. So this function will always map the agent and the opponent on every node except the lifts. And the successor function, we can see them as the edges of the tree. What action leads to what trace node or terminal node. The utility vector, which gives information about how good a state is for some player, and I, which is a vector with information which contains moves or spreads of the ith player Pokemon, something like what we know and what we don't know about the Pokemon. I have chosen 3 algorithms to test their abilities in this game. The first one is the min-max algorithm, which has the state of the game given by the information discussed above, the active Pokemon, reserve Pokemon, and so on. We have 9 possible actions, the 4 moves that the active Pokemon can do, and the switches that lead up to at least 16 possible states to the stochasticity of the game. Because we have simultaneous turns, we do an iteration for both the min and the max parents of the tree, leading to 16 to the power 2 states per iteration. So a maximum depth regulator is taken into consideration as Pokemon games have at least 15 to 20 turns on average. I also used alpha-beta pruning, and the utility function of the game is kind of complicated. So I gave it an equation to calculate it. I'll go as fast as I can through the elements. Hopefully it's not too complicated. Pokemons represent the set of all present Pokemons active or reserved in the Pokemon battle, as P is just one Pokemon. P that alive is either 0 or 1, whether the Pokemon has fainted or not. So if we take it into consideration or not, P that team is 1 or 2, so that we can add or subtract from the utility. Current HP is the percentage that the Pokemon has as HP. P.BO is the sum of all boosters score, some constants added, chosen by me to that are present in the Pokemon B. P.status is kind of the same with P.BO, but refers to the statuses of a Pokemon. Conditions refer to all side conditions present in the game or weather. And they also have an user side or opponent side for most of them. And their scores are, again, constants chosen by me to represent how much it influences the game. The second algorithm is the Monte Carlo tree search, which has for a main operation the selection operation, which starts from the current states and chooses to select nodes, children, based on their maximum USB value, until he gets to an leaf node on which he does an expansion operation that generates all states that can happen, but we take into consideration only those that the opponent chooses to maximize his utility. The simulation operation visits the leaf node randomly generated by the expansion operation and returns its utility. And the backup operation goes back to the root on the same path that was chosen by the selection operation and updates the USB values of every node. The advantage of using Monte Carlo tree search over min-max is the smarter manner in choosing the selection space to search, letting the most the better moves to explore more, and the ones that are not so good to are kind of ignored because they don't lead to our maximum utility. This algorithm searches deeper and so looks for more moves. But as the min-max algorithm, it requires a huge amount of memory to have the tree generated, and a lot of time to find the optimal state, which is a drawback in Pokemon battles, as we have a clock for turns as in chess. The third and final algorithm is the Q-learning algorithm, which it's a learning algorithm that needs all the states of that can happen in any game. So to reduce the dimensionality, I have chosen the 7th generation of OU tier of Pokemon, which has 665 Pokemons, and I have trained it on only one team. That means 6 Pokemons, resulting in a matrix of around 4,000 possible states. Okay, I'll go kind of faster. We have the actions. The reward is calculated based on the damage done, not taking into account some other strategies. The training and parameters and how many games I've played are shown this slide. And for experiments and results, the agents have played against human players. Their scores were noted. The most important one is being the ELO. We can see that min-max agent has the higher ELO on the 50 games that have played. ELO is kind of like a rank like in chess. And I have also test them against each other. The funny thing is that Monte Carlo Tree Search had more wins against the min-max, but the min-max had a higher ELO against human players. As a conclusion and future work, the results classify the Monte Carlo Tree Search and the min-max agents as average players, while the Q-learning as a beginner. For Monte Carlo Tree Search and min-max, some additions or changes that can be done are fine-tuned to the constants, the scores that I have told, and an approximation function will be good for searching deeper into the tree. For Q-learning, a different reward function, as this one takes into account just the damage done and ignores some long-term strategies. More time spent on training, because it needs to have a lot more time spent on the trading to find a optimal policy, and maybe a hybrid mode where first it starts with a learning approach and then with a searching one, because as the game goes on, the states of the game are reduced to are more narrow. Thank you for listening. So if one is a completely new player which doesn't know details about the game, and then is a, let's say, world champion, like the difficulties on the scale. Okay, so most of them I think are on the 5 or 6. I think Monte Carlo Tree Search is on the 6 and min-max on the 5. And the Q-learning, I think it goes on a 2, maybe 3, but with indulgence. Most of the algorithms in the literature do not fight against the human players, or if they do, they have kind of a similar ELO around 1040. I don't think I have seen more than 1500, but most of it have agents that fought each other. A knowledge-based system compared to a Q-learning, or different searching algorithms fighting against each other. So most of them are AIs, algorithms that fight with other algorithms, not with humans.
No more questions, so we can move to the next presentation. Mr. Laszlo Csople, please, with the paper Pandora Undelete Text File Recovery on X3 and X4 file systems. Please.
Okay, so as mentioned, my thesis was about deleted file recovery on the ext3 and ext4 file system. Let's first see what this project is really about. So the purpose of the project was to create a solution to identify and recover deleted files on the ext3 and ext4 file system. The project had the following objectives. First, an analysis of existing file recovery solutions for Windows and Linux file systems. Second, an elaboration of a file recovery method to solve the limitations of the existing solutions. And finally, to provide an implementation of the method and the testing framework to validate the proposed approach. So file system analysis can be categorized into two main categories. First, there are traditional methods which use file system metadata to recover files. These methods take advantage of the directory and file structures that are located on the disk and don't necessarily consider the file contents. These methods can fail if the file system metadata is damaged. For example, if the file table is damaged, there could be a possibility that nothing can be recovered. The second type of methods are file carving based. These methods are file system agnostic. They don't really care on which type of file system they are working on, and they try to reconstruct the files based on their content and signatures. For example, digital images have a certain structure that makes them quite easily identifiable in the data. These methods can recover data even if the system is corrupted, mostly because they don't necessarily consider the metadata that is located there. But they can be less reliable, especially if the recovered files are large and are fragmented. First of all, in order to understand the solution, we first need to take a look into the ext file system. ext is the extended file system and has been the default file system on most Linux distributions since it has been released. A journal was introduced in ext3 in order to provide transactionality to the file system and a faster recovery time after system crashes. In ext, each file is represented by inodes, and the file system is divided into blocks, which are then grouped together into block groups. We can see in this figure an overview of the file system and its structures. Now let's take a little bit of a look of how files are actually stored in the file system. First of all, there is a directory file which contains a large array of directory entries. And each directory entry contains a name and an inode number, which can be used to identify and locate on the disk the metadata that is related to the file. The inode, index node, is a container of metadata, and it contains information such as the size of the file, permissions, link counts, and different timestamps. It also contains an array of pointers, which can be used to locate the data blocks in the file system. These data blocks are the actual part in which the file's contents is stored. Besides these three components, there is also a file system metadata layer in which there are two bitmaps, an inode bitmap and a block bitmap. These serve the purpose of keeping track of which inodes or blocks are currently in use and which are not. So a value of 1 in the bitmap means that that inode or block is currently in use, and the value of 0 means that is not in use. Now that we've seen a little bit how a file is stored in the ext file system, let's take a look at what happens when a file is deleted. So in this example, we're deleting the recover.c file. And as you can see here, what actually happens with the directory entry, that is, it somehow gets swallowed by the directory entry that is located directly before it. I will explain in a minute a bit more about this process. The second change is in the inode. And here, the size field of the inode is initialized to 0. The deletion time is set to the time when the actual file deletion occurred. And every single block pointer in the array gets initialized to 0, so that we have no way of knowing where the file's data is located. Also in the bitmaps, the bits corresponding to the deleted inode and each bit corresponding to the data blocks of the file are set to 0, meaning that they are currently not in use, and when a new file is created, its data and inode can be placed into one of these empty spaces. Please note that the file's data is not actually erased. It's untouched by the deletion process, but just the pointers which help us to locate it are set to 0. So every data is still there, but just hidden. So I've mentioned that the directory entry gets swallowed by the directory entry that is before it. Let's take a little bit a look into what this actually means. So as I said, directories are just a linear array of directory entries. Here you can see two directory entries located one after the other. Most directory entries contain also a so-called slack space. This slack space are just bytes, which are not currently having any meaningful value, but they are there in case the name of a directory entry needs to grow or shrink. And what happens when a directory entry is deleted, in this example, the blue one, is that this directory entry will become part of the slack space of the directory entry that is located before it. So all the bytes are still there, unchanged, but now they are marked as unused in a sort of void space. So now that we've seen what happens when a file is deleted, we can raise the following questions. First of all, how to identify deleted files. Second, after identifying these deleted files, how can we recover the data blocks of these deleted files to get back the file content? And third, we need a way to recover the paths of these deleted files because they are separately stored from the other metadata of the file. And I provided the following solutions to these challenges. First of all, to identify the deleted files, we will just simply take a look into the inode table, which contains all the inodes of the file system, and select those ones which have the deletion time different to 0 and the size 0. Then, to recover the data blocks, we will use the journal. I've mentioned that there is a journal in the ext3 and ext4 file systems. This is just a collection of transactions, and each transaction contains metadata that is to be changed in the file system. And we can search actually these transactions to find older versions of the deleted inodes in which the inode size is not 0 and the deletion time is 0. And after recovering these older versions of the inodes, we can just follow the data pointers, which are still accessible there, to recover the old data blocks of the file. And finally, to recover the paths of the deleted files, we will search the slack spaces of those directory entries to actually locate those old directory entries which are marked as unused, but are still there. And putting it all together, this is our implementation. As you can see, first we will take a look into the inode table, recover the inode numbers. As a second step, from the journal, we will recover the inode version and then the file content. And the final step involves searching the directory slack spaces to recover old file names, and from there to reconstruct the path of the recovered deleted file. Now that I've explained a bit how our solution works, let's see about the testing and results. The testing of our implementation was done on a virtual machine on an ext3 partition, which was backed by a loop device. We implemented a tester application, which integrates the written library and keeps track of the results. We also have two types of testing scenarios, a basic test cases and advanced test cases. The basic test cases are just used to validate the implementation. It consists of three simple steps. First, we create a number of files in the root directory of the aforementioned new partition. We delete all of them in the order they were created, and then run the tool to recover them. You can see here the results from running 20 basic test cases, each having between 50 and 1,000 files, and each file having the size of 500 bytes. You can see here the worst, the best, and the average results. And based on these data, we can see that all our results are close to 100%, which is considered quite good. Then moving on to the advanced test cases. These are used to test the recovery performance in near real-life scenarios. These are still synthetic test cases, but they try to imitate the normal behavior of a file system during its lifetime. So an advanced test case has the following steps. First, we generate a number of directories in the partition. Then we generate a number of files in these created directories. We'll resize, rename, and move some of these files. Then delete some of the files and directories, and finally run the tool to recover them and check the performance. You can see in this graph results of the testing with the advanced test cases, and in this graph we have correlated the number of deleted files to the percentage of recovered inodes, recovered data, and recovered paths. And one can observe that as the number of deleted files increases, the performance of recovery decreases for recovered inodes and data, but it stays somewhat average for recovery of paths. And let's see why this can happen. So, as I said, the number of recoverable files decreases as the number of deleted files increases. And one possible cause of this can be that the journal has a limited size and is a circular log of transactions. This means that as the journal gets full, older transactions are overwritten by new ones. And this means that there's a big possibility that if the journal is small and there are a lot of deleted files, we won't be able to find transactions which contain older versions of the inodes that were firstly deleted. Secondly, I've mentioned that the percentage of recovered paths is quite poor. And one possible cause that we thought of for this is actually involved with the file renaming process. I've mentioned that every directory entry has a slack space. And when the file name needs to grow, the file name actually borrows some bytes from the slack space. So because in the advanced test cases we actually rename files, there could be a possibility in which the slack bytes are overwritten with the file name, and we are unable anymore to locate all directory entries. This is one possibility that we thought of, but we actually need further investigation to prove or disprove this hypothesis. And as conclusion, we have designed and implemented a deleted file recovery algorithm. We presented a new method of recovering the paths of deleted files. And finally, we also provided a design of a repeatable near-life testing procedure with the advanced test cases. And as further improvements, we would like to improve the reliability of recovered files to have more relevant data returned to the user of the library. We would like to better treat the corner case scenarios which could occur. Another interesting approach would be combining our solution with file carving techniques, again to improve the reliability of recovered files. Also, further research regarding the operations of the file system could be conducted to better understand the mechanisms that happen during file deletion and the way in which we can improve on our solution. This was my presentation. Thank you for your attention.
Thank you. Questions, please.
I would have a question. Once you restore the inode and get the pointers back, do you check to see if the data hasn't been overwritten in the meanwhile?
Yes. So what actually happens is when we recover the old inodes from the journal, let me just see if I have something in the backup slide. Yeah, so we recover the inodes from the journal, we recover the pointers, and then we take another look into those block bitmaps to see which blocks are currently not in use. If a block is in use, that means it is a high possibility that it was overwritten by another newly created file, so we will not return that block as recovered.
Okay, so that was my question as well. So now it's clear. If there are other questions.
Yes, so what is interesting that we actually performed tests on ext3 and ext4 file systems. And what we found is that because ext3 is a simpler file system having much less complicated structures, the performance there is very good. For example, in a test case with 1,000 files, we ran on ext3, the mean duration in which all of the files were recovered was somewhere between a few minutes. But on ext4, this time could be up to an hour for the same number of deleted files. But actually, in our implementation, we traded a little bit of recovery speed for the memory, because we wanted to make our solution memory efficient in order to use it on much less powerful machines. And this is why our recovery duration is a bit longer. But there are ways which can improve the recovery performance. For example, it can be implemented very easily in a multi-threaded environment.
Okay, thank you. I think we can move on to the next presentation.
Hello, can you hear me? Okay, thank you. So, as you heard, my name is Orshaya Search, and the title of my paper is User Authentication via Keystroke Sound using CME's LSTMs. Authentication is usually implemented with the use of passwords. However, that has certain security concerns. For instance, passwords can be found through dictionary text. And to somewhat remedy this problem, one can use multi-factor authentication, which means that the user has to present multiple pieces of proof to confirm their identity. And for multi-factor authentication, one could use keystroke sound very conveniently, because the user already has to type a password. So you might as well use that typing sound to further confirm their identity. And the other problem with a single login is that if the user leaves and the workstation is left unattended, then an intruder can gain access to the system. And if the software system that they're using requires a lot of typing, then we can also use continuous authentication to regularly check the keystroke sound of the user and to verify their identity based on that. And my goal was to implement continuous authentication in particular. There was some related work done in this area. There were two publications that dealt with the fusion of keystroke dynamics, which means timing information and the information of the specific keys that are typed, and the sound. And both of these dealt with static typing, which means that all the participants have to type the same text. So this is more suitable for multi-factor authentication rather than continuous. And the problem with the machine learning models that they used is that they require a separately trained model for each user. So when you add a lot of users, that's a lot of training. And if you create a large data set, you don't really have an advantage, because one model won't learn from the data of another participant. And there was one work done in continuous authentication with keystroke sound, and they actually published the dataset that I also used, and they have used k-means clustering to obtain a set of virtual letters, and then just use some mathematical formulas with the timing information to compute some scores. And that's how they created this biometric system. My solution has two parts. First, I have an audio feature extractor that deals with a meaningful representation of the audio, and then I have a neural network that actually makes the decision. As for the audio representation, I chose malfrequency substrate coefficients, because these are commonly used in all the related work and also in speech recognition. They are computed with by first computing Fourier transform, but then they are mapped onto the mass scale, which is a scale of pitches that more accurately represents the way we perceive sounds. And for the neural network architecture, I chose a Siamese model, which also consists of two parts. There is an embedding model that computes an embedding, a very compressed representation of the MFCCs, and then there is a similarity model that computes the similarity score. And for the embedding model, I chose a long short-term memory architecture, which is a type of recurrent neural network. And I chose a recurrent neural network because these are suitable for processing sequential data. And I chose the LSTM model in particular because they are good for learning long-term dependencies, because they implement a memory mechanism. So I already mentioned the data set that I used. This contains data from 50 participants, and I used 10 participants in the testing set, and I used the remaining 40 for training and validation with the 5-fold cross-validation technique. And all the models were implemented in Keras. And to compare the models, I used, to compare them and actually to evaluate the final model, I used two metrics. One is the equal error rate, which is the value at which the false acceptance rate and the false rejection rate are the same. And the other one is the receiver operating characteristic curve that you can see there, which is achieved by mapping the false acceptance rate against the false rejection rate. And I compared the models based on the value that is the area under this curve, which is always between 0 and 1, and the higher it is, the better the model is. First, I experimented with the loss function, and for that I designed an initial embedding model that has a single LSTM layer and two fully connected layers. I tried the contrastive, the triplet, quadruplet, binary cross-entropy loss functions, which are frequently used for Siamese neural networks. And in the end, I found that the contrastive function worked the best. And for this contrastive function, the similarity is computed with the squared Euclidean distance. So from the two arrays that's of size 16, the neural network computes the squared Euclidean distance. And then, as my model had quite high variance, I tried to add regularization first to the first fully connected layer of the two. In this way, I achieved only a slight improvement with L2 regularization. Then I tried also regularizing the LSTM layer, which worked out much better. And so I kept both regularization that I achieved with both of these experiments. Then I tried to increase the size of the model to potentially make the model capable of learning more, but this wasn't really that successful, so I kept the same model in the end. And then my final model consists of an LSTM layer that is regularized, a dense layer that is also regularized, another dense layer, which outputs the embedding. Then this computes the squared Euclidean distance, and from that I have a distance score. As for the results, I evaluated the model on the testing set consisting of the 10 participants. And in this way, I achieved an equal error rate of 1.28%, which evolved quite unpredictably on the testing set, as you can see there. And I also have the error C curve plotted there, and the area under it is 0.9995. So in the related work done by the publishers of the dataset, they've achieved an equal error rate of 11.7%, while I achieved one of 1.28%. But I should mention that in their testing set, there were 35 users, and in mine, there were 10. And also another difference is that they used for the enrollment soundstream data that is from restricted typing. So every user typed the same text, while I only used the unrestricted typing. Thank you for listening, and if you have any questions, please feel free to ask.
I have a question. So, are you sure the users in general are typing in a consistent fashion so that you can recognize the typing habits?
Well, I can't be sure. I can only be sure of the type of text that they used in this data set, which, well, every user typed approximately 5 to 7 minutes, and they have to type a letter to their family. So, for example, if someone would be writing code, I think that would be very different from the way someone types a letter, because there's a lot of copy pasting and so on. So I think that would be different, and there should be a data set constructed to also test this.
Okay, thank you.
No, so in the data set, they used only one microphone and only one keyboard, so it only works for that. And I don't think it would work with other keyboards and other microphones. But so the model that I developed can't really be used in a real setting yet, because it's not trained on real data, it's trained on a very controlled set of data.
No more questions, so I think we can move on to Andrea Nicoleta Damsha with a paper titled Visual Acuity Analysis in Relation with OCT Data for AMD Patients. I hope you will tell us what these acronyms stand for.
So my name is Damsha Andrea Nicoleta, and today in this study I will present an analysis for the visual acuity with correlation to OCT data for patients that suffer from AMD disease. So to unravel the title, first starting with the AMD, or age-related macular degeneration, this is an eye disease that affects the retina, which is the layer responsible for our vision, and it represents the leading cause for blindness in the developed countries. Given the context of deep learning and the advances that it has made over the last years, the medical data, especially the imagery, has been proven to be profitable or give a substantial amount of information when analyzing the images and presenting a potential to be a helper in the professional medical treatment scenario, or maybe just analysis. So such informations that can be extracted using the deep learning models can as mentioned, can be used by the medical professionals, giving them guidance in the diagnosis and treatment process, but also can represent a benefit for the patient, because it can help them view and visualize their state and maybe understand the whole idea of the disease and how their eyes will be evolving. So to understand the bigger picture of the AMD at a global level, here I introduce some statistics. So in the US, there are 11 million people suffering from some form of AMD, and this number is expected to double by 2050. Globally, there are 170 million people suffering, and another statistic that is important for this disease is the fact that it has a progressive aspect. So as the time passes, the retina worsens. So, for example, for elders over 75 years old, there is a 30% chance to develop AMD. Another concept that is worth explaining and mentioning is the visual acuity. So this is basically a quantification of a patient's ability to clearly see from a distance. Probably most of the people have been tested in this type of setting where the patient has to be 20 feet or 6 meters apart from a chart with different sized letters. This chart is called the Shannon chart. Here I gave some examples because the actual formula is a bit harder to understand, so I presume that with some examples, this concept would be easier to understand. So for a healthy patient that is positioned at a 6 meter or 20 feet distance from this chart, if he sees clearly all the letters, then his visual acuity would be rated 20 by 20, and in equivalent of a numerical value would be 1. And for example, a patient that needs to approach to a distance of 6 meters to read the letters that that a normal patient that has a healthy eye could see from a distance of 12 meters, then his visual acuity would be rated at 20 by 40, and in a numerical real value would be 0.5. So given this conversion from notation in real value, the range of visual acuity considered in the study is 0 and 1. the AMD reflected in OCT images. Here on the left, there can be seen two different types of retina that actually belong to the same patient. One is the left one is of a healthy eye with a 20 by 20 visual acuity, and the right one has an advanced stage of AMD, and its visual acuity is near to blindness, so the vision loss is quite significant. So this retina, so here there can be seen the stacked layers of the retina, and here the retinal space that has been formed. This state of the retina can be evaluated by the medical professionals with the technology of optical coherence tomography, which is a non-invasive one, and acquires images of the retinal layers and some additional data as well. Referring to the available data for this study. In this study, there were included collected data from the Emergency County Hospital here in Cluj. There were tracked a total of 94 patients, and they are having a varying number of visits between 1 and 15. Also, for the visits, they were tested or analyzed with the OCT. Their visual acuity was also tracked, so that's what we are going to use in this study. Something to mention is the fact that this study is made after the collection of the data, in the sense that the methodology was not a consistent one. So there exist some deficiencies in the data set, like the variable numbers of visits and the variable length of time between the visits of a patient. Here on the bottom, there can be seen an animation with the 25 images. So when using the Heidelberg Spectralis, for example, the machine that was used in the study, for each eye and each visit, it is generated the 25 images that comprise the volume of the retina, and as well the software generates an XML file with numerical information regarding the thicknesses of the retina. So as for the XML data here on the left, it is illustrated the idea of acquiring this numerical data. So the zones in superior, inferior, temporal, and nasal, and the central area, they all present thicknesses and volumes, and these values can be calculated by the machine and structured as mentioned in XML hierarchy. So given the available data, the approaches for the architectures that are going to be used are the following. Multi-layer perceptron, recurrent neural network, and also convolutional neural network. For the first architecture, the multi-layered perceptron, this is one of the most simple types of artificial neural network. It comprises of stacked dense layers of neurons. And with this architecture, the input was the numerical real values for the retinal areas that were previously mentioned. And the output was the prediction of the visual acuity that is associated to these values. And the visual acuity is predicted in its decimal format. For this model, the metrics that was used is the mean absolute error, and it reached 0.2. And given the fact that the range for the visual acuity is 0.1, this model does not provide a good enough performance. The next architecture that was used was the recurrent neural network, having in mind the idea that it can model temporal data for sequences. So the actual architecture implemented was long short-term memory, LSTM. And the idea was to have the sequences represent the visits of the patients. So a visit is represented by the retinal thicknesses and their associated visual acuity. And the prediction and the output of this model is trying to predict the evolution of the retina in a hypothetical next visit. So given the current evolution, the model should be able to predict if it gets worse or it remains stagnant. The sequences here that were considered were of 3 visits. So the first 2 visits represent the evolution, and the third is what we try to predict. The chronological ordering of the data is also very important so that the evolution can be conserved. After the processing of the data, there were left 150 data points used for training, and the metric of mean absolute error reached 0.09. On the left, there are some illustration of the prediction of this model. So the red dotted line represents the actual visual acuity value, and the blue one represents the predicted one. Here, it can be seen the interval. So, for example, from 0.05 to 0.4, the variation between the prediction and the actual value here is maybe in the range of 0.1. The third architecture that was considered is the convolutional neural net. These types of nets are known for being performant when given image data. So, of course, OCT images were used in this sense. Because there are 25 images for each eye for each visit of the patients, one strategy for reducing the large data set was to use a classifier previously implemented with the backbone of DenseNet that classifies the images in these 4 classes mentioned: drusen, diabetic macular edema, choroidal neurovascularization, and the normal eye. And using this classifier, out of the 25 OCTs, there were selected the worst 3, which means the ones that had the lowest probability for the normal class, in order to have the most relevant ones when predicting the visual acuity of the patient. This supervised learning has as well the assigned visual acuity for the single OCT image. So as the input for the single OCT image, it was predicted the visual acuity associated to it. Here is the structure as well. Here was used the transfer learning with the DenseNet. The performance reached 0.18 for mean absolute error and presents a small improvement in comparison to the numerical data. Also, something worth mentioning is the fact that the classifier previously mentioned uses the Kermani dataset and has a really high accuracy, given the fact that the CNN is way more complex and has a larger dataset. A convolutional neural network that is implemented and with the idea in mind of being used in the future is the classification of images based on the patient they belong to. So this task can be viewed as a surrogate or subtask that is meant to be integrated in a future architecture of multi-input, where the feature identified in the images, because having a accuracy of 0.85, the network manages to identify relevant information about the retina. So using this information, these extracted features, the goal is to integrate it into a multi-input network that could get as an input maybe the three worst images mentioned earlier, and also use the classification that establishes the images to which patient it belongs to, and so the loss can be calculated taking into account both subtasks. As of right now, this is implemented, but it doesn't have very good results. In conclusion, some ideas that represents an overall view of the study are the fact that the increased complexity in the study is given by the large number of images per eye. So maybe a better improvement would be to consider this as a whole, as a volume, to see the data as the 25 images as a whole. Another thing worth mentioning is the fact that this study tried to use real-world existing data, and this yields not or lower performance in the models. And also the fact that the classifying...
Okay, I think we got the picture.
Okay.
You know, we have seen the presentation. We have to move to questions. So please, questions, please.
Regarding the future work architecture. The future work architecture has the main idea of combining the images, because, as mentioned before, maybe it's not the most performant or accurate approach to treat the images individual, as they are part of the same state of the retina. So that architecture has in mind of treating these images, and first we considered three at once, and using the feature learned by the already implemented classifier. And as of right now, the architecture is implemented, but it is not integrated with the classification surrogate task, and so the results are not exactly relevant.
Thank you. I think we have to move to the next presentation, so please.
Yes, hello, can you see me? Can you hear me? Excellent. Hello, my name is Sharkozy Melissa Alexandra, and I will be talking about facial recognition using convolutional neural networks. Today I want to talk about what facial recognition is, about related work that inspired me. I want to propose my approach, and I want to present a series of experiments that I've been working on. Face recognition is a biometric recognition task that consists in identifying a person based only on their facial features. So we can divide this problem into two different tasks. We have the verification task, which is a one-to-one problem, where we receive two input pictures and we have to tell whether the same person is in both of the pictures or not. And we have the identification problem, which is a one-to-n problem, and we receive an input picture and an associated database, and we have to tell whether the person in the input picture appears in our database or not, and who that person is, if so. We can use face recognition in areas like law enforcement, banking, airport, and borderline security. We can also use it to unlock our phones or even go through a check-in process. Facial recognition systems follow a conventional pipeline consisting of 4 steps. First, we can see in this scheme on the left side, the first step is face detection, so the face is being detected and then cropped. The second step, which is optional, is face alignment. It's recommended to align the faces in order for the classifier to extract the features better. The third step can be seen in this square. We have the face processing and face extraction, feature extraction step. During this step, we usually use convolutional neural networks in order to extract relevant facial features in order for later classifying them. And that is the fourth step, the classification step. Labeled faces in the wild is a public face recognition benchmark. It is the most used face recognition benchmark, and it's a database containing 13,000 annotated RGB pictures of celebrities. As for related work, we have the deep face model proposed by Facebook in 2014. They used 3D face modeling based on fiducial points, and we can see in this scheme in the left side, they called this process frontalization. They achieved 97.35% accuracy on labeled faces in the wild, which is a little bit worse than the human accuracy for facial recognition. In 2015, we have the Google proposed FaceNet model. They tried to predict embeddings associated for each identity, and we can use these embeddings for face recognition and face clustering. They proposed a new loss function called triplet loss that we can see in the figure below. And they achieved 99.63 accuracy, and it's also worth mentioning that they use a private database containing 200 million images of 8 million identities. In 2017, we have the sphere face model, and the authors suggested that pairing the softmax loss with the Euclidean distance was not natural, and they rewrote the softmax loss from an angular perspective and proposed a new loss function called a softmax loss. We can see in the figure below that by modifying this softmax loss, they were able to condense the representations in both Euclidean space on the left side of each figure and the angular space in order to make the classification more accurate. They achieved a 99.42% accuracy on labeled faces in the wild. My solution was to focus a little bit more on the face detection task, as it is the first step in the recognition process. And I also proposed a new concept called the enlargement factor. So following the conventional pipeline, I developed a face recognition system based on 3 components. First, the face is detected using multitask cascaded convolutional neural networks. After that, I applied the enlargement factor, which I will talk about a little bit later. Then the second component is the inception CNN face encoder, after which I used 2 different approaches for the face classification task, a distance-based one and a softmax-based one. For multitask cascaded convolutional neural networks, these are an ensemble of 3 small networks. The input image is being resized in order to create an image pyramid that we can see on the first row in the picture on the right side. This image pyramid is being fed into the first network, that is the proposal network, where bounding boxes are proposed for the face detection task. After that, we have the refinement network, which tries to unify these small bounding boxes in order to create larger ones. And the final network, the output network, it refines the bounding box even more in order to detect only the faces and in addition, facial landmarks, 5 facial landmarks are being localized. We have the eyes, the nose, and the corner of the mouth. Yes. The enlargement factor was something that I thought about, and it refers to the moment of the face crop. We want to make the crops larger, and I tried to illustrate on the right side with a darker blue. We have the previously computed detected face, and with light blue we have the enlarged face. And with the red arrows we can see how much the face was actually enlarged. And on the left side of the slide we see the altered height and width dimensions. Here is a picture. I tried to illustrate visually the impact of this enlargement factor, and I also want to point it out that for larger values of the enlargement factor, actually the crop is being enlarged by a smaller amount. As for larger values, smaller values of the enlargement factor, where the face is being cropped by a larger amount. For the second component in the pipeline, I used the GoogleNet CNN architecture. This is an architecture that uses inception blocks that are basically more convolutional blocks stacked together in order to give the network the chance to extract relevant features of different complexities at each level in the network. So basically, the network is trying to choose the best architecture for the task using different convolutional blocks. We can see in the figure below that there are 2 different implementations for the inception module. We have on the left side a more naive version that doesn't consider computational costs, and on the right side they used one-by-one convolutions in order to reduce the computational costs. And here I drew the architecture of the face encoder that I used. We can see the inception blocks with red, with an orange-red color. I also have with green the reduction blocks, and a stem block, which is a sequence of convolutional networks with yellow. And the final layer is a dense 128 dimensional layer. For the classification task, I used 2 different approaches, the distance-based and the softmax-based. For the distance-based, what happens is that the inception encoder is used in order to compute a 128-dimensional embedding for each training sample, and that those embeddings will be used in order to perform the classification. As metrics, I used the Euclidean distance and the cosine similarity. And for the softmax-based approach, I performed transfer learning on the inception encoder by removing the last layer, the 128-dimensional dense layer, and replacing it with a softmax layer in order to perform the classification. As for loss functions, I use the cross-entropy loss and 3 different state-of-the-art face recognition loss functions: sphere face, cos face, and arc face. Here are the formulas for the metrics that I used. We have the Euclidean distance, the cosine similarity, the difference between them being that while Euclidean distance tries to calculate how far away 2 vectors are in the Euclidean space, the cosine similarity tries to calculate how similar 2 different vectors are in an angular space. And for the softmax-based loss function, starting from the well-known cross-entropy loss function, the authors of sphere face tried to rewrite it from an angular perspective by introducing a hyperparameter m called multiplicative angular margin. Following the sphere face approach, the authors of cos face developed a new loss function called Okay. So we have the cause phase and the arc phase, and I just want to mention that these two are the current state of the art in face recognition, with arc phase having an accuracy of 99.83%. For my experiments, I use labeled faces in the wild. For data normalization, I use the Z-score visible on the right side. And I trained 8 models that use the distance-based metrics and 16 models that use the softmax-based metrics. And here are my results. For the distance-based, we can see that for an enlargement factor of 8, we had the best results. And for the softmax-based approach, I chose both the accuracy and the precision. And we can see that in terms of accuracy, the cross-entropy function converged faster and reached better results. But the state-of-the-art recognition loss functions are better in precision. I also implemented the cosine similarity model using an enlargement factor of 8 in a client-server mobile application called Facial Scanner. And for conclusions, face recognition is a domain that evolves every day, and it has a great chance of becoming a safe and reliable authentication method, especially nowadays in the context of the COVID-19 pandemic. And as the most popular face recognition models obtained great results using various CNN architectures, the purpose of this case study was to focus on the impact that face detection has on the recognition task, and also to compare different loss functions. Here are some references, and thank you for your attention. Yes, sure.
Okay, so I think there are no questions, so maybe we can proceed with the next presentation.
Thank you so much.
Thank you for the presentation, Melissa. And we move to one small observation still, Melissa and others. I believe that you allocated a bit too much space for the related work. Almost maybe for the real actual diploma project or what you will have, you could consider allocating a bit less time for this, because what's important is your contribution. This is what we really want to know.
Okay, understood. Thank you so much.
Yeah. So Robert, please, Robert Varati or Gabriel, who is presenting?
I'm present. So I will show.
Okay, so Robert, please proceed.
Okay. Can you see my presentation?
Yes, please proceed.
Okay. Hello everyone, my name is Varadi Robert, and today I will present my paper entitled Infrastructure for Capturing and Persisting Virtualization-Specific Events Triggered by Ingest Process Executions for Behavior-Based Analysis. As you all know, security threats nowadays are mainly represented by computer viruses. Antiviruses have been devised along the time in order to deal with such security threats. However, they suffer from a big disadvantage, and that is the case when a rootkit gains access over the kernel of the OS the security solution is based on. The solution is to move the security services outside of the monitored OS, and this is achieved by building intrusion detection systems deployed into a hypervisor. There is also a tendency to move towards machine learning methods when building an IDS or an intrusion detection system. The objectives of this work is to collect information about both system calls and virtualization related events. Also to control the events that are intercepted, as well as the list of processes for which we want to intercept those events. And another important point is to be able to monitor for a process of interest, also the child process that it creates. Why do we need such a system? Well, because intrusion detection systems need large and relevant data sets in order to be able to build the ML models. However, such data sets are there are only a few and small data sets available publicly, and also commercial and open source hypervisors that are popular offer only high-level statistics about the events that they intercept. And we believe that detailed information on virtualization events could result in better security solutions. The proposed approach consists of a monitored machine in which we deploy an in-guest user mode virtual machine introspection component, an in-guest kernel mode virtual machine introspection component. This monitored machine will be actually a virtual machine managed by a hypervisor in which we have an in-host VMI component and a VM management module. And we will have an analysis machine into which we deploy a collector module and a control module. This is the highest level architecture of the system. You can see here the monitored machine, the hypervisor, and the analysis machine. And I will go into detail for each individual component of the system. The first one, inside the monitor machine, is the in-guest user mode VMI component, which is deployed in the form of command interpreter with which a user can interact, or it can read scripts from a script file in order to automate some of the tests. It also communicates with the in-guest kernel mode VMI component and the in-host VMI component through two different communication channels. The next component is the in-guest kernel mode VMI component, which is deployed in the form of a driver, and it contains a list of processes that we want to monitor. And the idea behind this component is that if a process that is already monitored tries to create a child process, this creation is recorded, and as a result, the child process's ID is added to the list. And whenever a process that is monitored wants to terminate its execution, this process ID is removed from the list. Also, this list must be always, on each operation, must be synchronized with the internal structures of the in-host VMI component. That's why it has to also communicate with the hypervisor. Okay, the central component of the entire infrastructure is represented by the in-host VMI component, which is a module of the hypervisor, and it consists of an event interception submodule, which is able to intercept VM exits generated from the monitored machine, or comments that come from the in-guest component. These intercepted events are filtered, and if the event information matches some filtering rules, at least one filtering rule, those events are forwarded to the analysis machine. On the analysis machine, we have infrastructure control application, which has the responsibility of encapsulating the functionality of the whole infrastructure under one command line interface. The next relevant component is the virtual machine control service, which receives generic virtual machine management commands and transforms them into specific VM management commands. Why is this important? Because we don't want the other components of the infrastructure to know the actual implementation of the VM management module. This can be a module from the hypervisor, or can be a commercial hypervisor as well. So we want to abstract this interface away. Then the log filtering service listens for logs generated by the in-host VMI component, and from those logs, it identifies virtualization events or generic VM management comments, and these events or comments eventually reach to the event collector service or to the virtual machine control service. Okay, and the final component of the architecture is the event collector service, which has a layered architecture in order for good extensibility, and it listens for virtualization events coming from the log filtering service and persists them into a database, into a structured way. We've also done some functionality and performance testing. This is the test setup. The testing was done from a single machine, so we needed a hypervisor that is able to support multiple virtual machines, and which could be installed onto a host OS. So we chose a VM workstation for it, and the VM management module is actually the API the VM workstation provides. So this is where we control the VMs that we want to start. Okay, in order to easily deploy our solution, we use network boot from a PXE server, so the hypervisor can be booted from there, and the whole interception module is enclosed into a special VM by this VM workstation virtualization software. It is worth mentioning that the monitored OS is actually a Windows 10 OS on 64 bits. And the testing phase starts by starting the infrastructure control application. These are the comments that we enter, the prompt that it displays. This is the command prompt from the guest machine. The first step is to start the driver. After the driver is started, we can start a short, small application in order to record some events. These are the comments that are sent to the hypervisor and to the driver by the ingest user mode VMI component. Here we can see the way the hypervisor processes the incoming requests, and as well how does it intercepts the events. So this is, for example, a system call. This is an event generated by a read random value instruction, and this is generated by a read random seed value instruction. After the test, after we finish the test, we can go to the database and run some queries in order to make sure that the events were persisted, and we can see them here. The test application started a child process just to demonstrate the functionality of the driver. Then here we can see the other virtualization events, namely the read random seed and read random value event collected. As I mentioned before, we also performed some performance tests. Those were done using PassMark, which assigns scores. So these numbers here actually represent scores assigned by the benchmark, and the higher the score, the better the performance. The reference measurement was done for the guest OS running without any virtualization. Then we started the hypervisor, but no interception was activated. We continued by starting the interception, and we concluded by starting the filtering and the forwarding. As you can see, for the CPU and the disk operations, the performance varies as we start the different layering processes, processing layers, which means that these operations are influenced by system calls. In the same time, memory operations are very
yes, it's very visible. Please move on with the presentation. The time is pressing us.
Okay, these are the results for the 2D operations, the 3D operations. And an interesting fact was to measure the relative decrease in performance. As we can see, when adding the hypervisor, the decrease in performance was very small because the majority of instructions still runs on the real CPU. However, when adding the interception of the system calls, the performance decrease is bigger. And that's mainly because of the high exit rate generated by the system calls, as well as the large number of clock cycles needed for the exit. And when adding the filtering rules and the forwarding, the performance penalty comes from the traversal of the list of filtering rules and the writing to the serial port. This is actually what I've mentioned here. And as conclusions, I would like to point out some strong points. That's the ability to control the interception of the events from ingress components. We can acquire detailed information for each transitional event. There is a good interoperability between modules because communication relies on interfaces. The information is persisted in a structured way, and also individual components are easily extensible. The limitations would be the performance overhead due to the high VM exit rate, and the fact that the infrastructure cannot label the run samples as being malicious or non-malicious. For this phase, we will need external tools which can achieve automatic labeling from software events.
Okay, thank you very much. So, questions, please. Short questions. I have a short question. So, can you see in what scenario, in what real life scenario, do you see such a solution deployed?
I would see such a solution deployed in, for example, in cloud infrastructures where we want to manage multiple virtual machines and don't want to have like antiviruses there, because if a rootkit reaches the kernel of the OS running on those machines, the antivirus wouldn't be effective anymore. So,
okay, I understand. It's a plausible scenario. Thank you very much. Let's move to the next presentation, please.
Yeah, hello there. I hope you can see me and hear me clearly. I'm gonna try to share my screen real quick. So can you see the PowerPoint? Okay, great. Okay, then I'm gonna start. So thank you very much for the introduction. It's great to be here again. Thank you for having me. I'm here to present my master's thesis, so entitled Table Detection Medical Tubes Using Computer Vision and Artificial Intelligence. This is developed with my professor Sakara Christian, and a project that I was fortunate enough to work on at Stratec Biomedical Romania. And without further ado, let's start to see what this is all about. So working in the medical analysis field, so industrial laboratory analysis, things change pretty fast. So as you all probably know, nowadays medical analysis are being done by robots and instruments, and thus changes need to be made in order to automate this process, more specifically identify samples and have machine readable labels that can identify samples and link them to patients. And the current way this is done is at the point of collection, there are the blood samples or any other biological samples are being labeled with the specific identifier that identifies the patient. So before this, they used to write, I'm sure you all know if you ever had an analysis, blood analysis, and you used to write the name on the tube, but nowadays it's all machine driven. And of course, because of this, so a new niche comes up. So which pretty much means, okay, we need to have better and faster machine reading techniques for sample identifiers. So the way it's been done until now, as you could probably see, it's one-dimensional barcodes that are being used to encode patient identifiers. But the industry and medical labs are slowly transitioning to more advanced techniques such as QR codes because of their density of information and the advantages that image processing and computer vision can have for this type of context. So besides identifying a barcode or two-dimensional barcode, you can also extract multiple features of the tube, multiple relevant features that can help on with the automation process. So, for example, you can infer the cap type, tube dimensions, tube types for the liquid fill level, which is also a hot topic in this field. And one of those features, so the one I've been working on, is label detection. So without extracting information from it, just simply detecting if a tube has or doesn't have a label. So here you can see some examples from the data set I required. So we have simple medical tubes, currently empty, but it's beside the void. So we have tubes with no label, with one label, different types of label we can have here. So there's barcode labels, there's standard tube providers labels where they also maybe write their names of the patients, and there's tubes with two labels. And why this is useful is it's in the tube scanning process, you can actually infer multiple features coupled with the detection of this label. So for example, you can pace up the process if you don't find the label, so you cannot find a barcode or an identifier and everything, and you can speed up the whole analysis project. Also, you can tell if you can analyze the liquid level. So, for example, if you have a label that covers the whole tube, then you cannot see where the liquid is, so you don't waste time with that. And most importantly, you can identify false positive identifiers and barcodes, such as in this example. That's also a big problem, and it's a sad outcome really, because it doesn't happen that often, but thanks to human error, if there's separate identifiers and tubes, it can lead to misdiagnosis and pretty horrible consequences. What's also worth mentioning here is that for this project, we have the advantage of acquiring multiple images from multiple points of views of a tube. So we're not restricted to classifying just one image and just say, okay, does this one have a label or not? We have multiple images, and then we can infer this. And for this, we chose to use a median average, which I'll get more on later. So talking about the hierarchy of label states here. So we have two big kind of classification points here in this tree. So there's the label presence. We want to determine if a tube has a label or not. So if it's absent or present, that's a binary classifier. We'd also like to count maybe the labels. So there's whole another classifier involved. So this one has three classes. So we have label absent, 0 labels, 1 label, or 2 labels. And finally, there's kind of a hybrid approach that was just for the purpose of the study. So creating a classifier with two binary models that could also predict 3 classes. So absent, 1 label, and 2 labels, but it has 2 binary models. Yeah, so for the actual implementation of these models, there's as I've chosen a pretty straightforward approach. So start with a couple of fully connected neural networks, switched on to convolutional neural networks because yeah, everybody says they do the job right. And I'm not going to get into too much detail about this. There's nothing really special about them, maybe just the results they provide. One interesting topic I like to touch on is they also need efficiency. So as I said, this kind of label detection, so feature detection, should take place in high-speed imaging platforms, so on medical device. So automation speed is everything for automation. So it needs to be not only accurate, but it needs to be fast. So for this, a separate, an additional thing we looked at is the speed, and more importantly, so this is directly correlated to the size of the network. And for the networks we presented, the majority of the parameters were kind of grouped at the first layer, and that's the image layer because the image is pretty big. So I created 4 different models with the input image resize factor. So starting from the original image down to 0.3, the resize factor, and you can see the drastic change in parameters, in the number of parameters, like an order of magnitude from the original image to the 0.3 factor. And we were going to compare these results in accuracy and in the speed of the inference time. On the topic of related work, we found a pretty similar context, a pretty similar problem in the paper real-time barcode detection and classification using deep learning, where the authors used the YOLO 9000, the famous YOLO network, to identify barcodes on labels. Although that's not really the same thing we're trying to do, it's pretty close, and we chose this as a reference because the YOLO is pretty much considered a state of the art in the object detection branch, and we're going to also compare our results to theirs. Yeah, so I've talked a lot about the approach and implementation, so let's see about some results right now. So the first thing that pops up, the pretty straightforward one, is the label presence binary model. So this one just discriminates between absent label and present label, and as you can see, the results were pretty good, scoring about 99% accuracy on single images. And as I mentioned, since we have multiple images, we can infer our prediction of the average median of these images turned out to a pretty awesome 100% in accuracy. On the label count model, so here we have the three different solutions compared. So there's the tertiary neural network, so that's the same as here. The hybrid approach I was talking about, and the CNN. And as you can tell from this graph, it looks like the fully connected ones are actually outperforming the CNN, surprisingly. There might be also a matter of retraining and a couple of different percents here and there, but what's important is it's that the results look really good. So for the tertiary classifiers, a more in-depth look of the performance metrics of these 3 models. One thing worth mentioning here, as you could probably see, so the no label class is looking pretty good because it's also extremely different than the other classes. So there were no problems encountered in classifying this one. Where the dip in accuracy comes from is the models confusing the 1 label and 2 label class. And as you can probably see, so given the high precision for the 1 label class and low recall, we can infer that the models, all of the models, are favoring the two label class. And I have actually I plotted some examples here to validate this theory. So you see most of them are through one label class images, while the models are predicted two labels. And in such examples, you could see here, it's really difficult. So it's basically impossible even for the human eye to tell. So you can have a label on the back of this tube and not see it. So and we have these kind of images in the data set, so to keep it as raw as possible, and it's understandable for the model to make such mistakes. We hope to correct this in the future since, sorry? Yeah. Okay, so the most important thing here is also the efficiency statistics. So as I mentioned, the 4 models with different resizes based on their accuracy and speed. So apparently the 0.5 model had had a sweet spot there in terms of accuracy, and also 11 milliseconds is really good compared to the CNN, like 8 times that. And I also compared this result to the YOLO model I was talking about, and as we see here, so the accuracy is pretty good compared to that. It's not really fair to look at the accuracy since it's not the same problem, but it's in the same domain. So we found that as a good sign, and the inference time is also really good. So 11 milliseconds. And yeah, coming to the conclusion, what I usually like to infer from this is less is more. So you don't really need the biggest models and the biggest networks to achieve good results. And sometimes it's important to achieve a middle ground of things. So thank you very much for your attention. I'm sorry if I overstepped the program. And now I'm waiting for questions if you have any curiosities. Yeah. So as I mentioned, the fortunate part about this problem is that it's a consistent error. So in the future, I'd like to try a weighted class approach, so a kind of bias training that favorizes a class even more than the other. And then, given that we have multiple images, we can infer our result from. Then we can account for this error, and then in reverse, favorize on the median average, favorize the other class. I hope that answers your question.
Okay, so thank you. Let's move to the next presentation.
Yeah, thank you very much.
Boda, with a paper titled Load Balancing Strategies and MLFQ Dynamic Priority Computation in Multiprocessor Systems. Please, Mr.
I hope you can see my presentation.
Of course we can. Please proceed.
Okay, so this is my presentation, like Professor Suciu said. Those are the topics that I will go over. I will start with a brief overview. So I work at the scheduler component of the operating system. This is a very important component as it has to manage access to the CPUs. It has to take into account thread priorities, and overall it just has to provide a fair and efficient scheduling strategy. That's very important because bad scheduling will inevitably lead to a bad management of the hardware resources and to a pretty significant degradation in performance. There are some methods that we can use to make sure that our scheduling is good. We could use load balancing and multi-level feedback queues. I will go into more detail into them shortly. So what I tried to accomplish with this project, as a side note, I worked on the HAL 9000 operating system, which is our university's OS, and I wanted to implement and study some load balancing approaches. I've mentioned them here. There's a pull and push. There's an approach that uses both at the same time, and we can also add a global balancing thread on top and see how that changes the results. I also wanted to implement MLFQ, which is used to deal with the dynamic priorities, and experiment a bit with the formula for priority computation, and of course to draw some conclusions from all of those tests. So load balancing. Load balancing, it's an operation that's used to distribute the workload evenly among the processors. So we want to avoid a situation where, for example, we have one CPU that's idle while another CPU is overloaded. There are two main approaches that we can use. Here on the left, you can see the pull approach, where when a CPU has the number of threads under a threshold, it will try to take a thread from another CPU. We also have the push balancing approach, which is kind of the opposite of the pull, because when CPU has the number of threads over a threshold, it will try to give some of the threads to another CPU. Other than that, we could also use a global balancing thread, which would be a periodic thread that will try to balance the threads between all the CPUs. So not just two CPUs like pull and push, but between all of them. In order to do this, that we basically have to stop scheduling at the system level. So it's in our interest to make this operation as short as possible. Now a bit about multi-level feedback queues. So those deal with dynamic priorities. Dynamic priority means that it's managed by the system and not set by the user, for example. And because it's set by the system, it will change constantly as the system progresses. So in this approach, instead of having one queue per processor where we store the threads that are ready to run, each processor has an array of queues which are ordered by priority. So when the scheduler wants to pick a new thread, it will simply go to the highest priority non-empty queue. We also have to take into account that since they're dynamic priorities, they will change often, so we have to move them accordingly between the threads. This is the priority computation formula that I used. It's taken from the Pintos OS, and I will briefly explain what those terms mean. So the first one, the priority, that's obviously the priority of the thread. Primax is the maximum priority that can be achieved in our system. In our case, that's 63 because we have 64 threads in our implementation, so priorities go from 0 to 63. Recent CPU, it's a measure of how much CPU time a thread has received recently. And finally, the nice value, it represents the tendency of a thread to either give some of its CPU time to another thread or to take some CPU time from other threads. In our implementation, this takes values between -20 and +20s. And the meaning is that negative values tend to take CPU time from other threads. So we would expect that threads that have a nice value, -20, -19, would get more CPU time than threads with, let's say, positive nice values. Okay, I will describe now a bit the tests, and then I'll show you the results. So for load balancing, I ran a fixed number of threads with the different load balancing strategies that I implemented. I measured the execution time, and then I also added a global balancing thread on top to see how that changes the results and to see if the overhead implied by this thread is justifiable. Okay, so here on the left, those are the load balancing strategies compared. Here with the blue line, this is when no strategy is used, and as we can see, it results in the highest execution times in here on the y-axis. Those two with red and green, they are the push and pull respectively. And what we can see from those is that the push strategy performs better for a lower system load, so when there are fewer threads in the system. But as the number of threads increases, the pull strategy becomes optimal. Also, I tried the combined strategy, so both push and pull depending on the state of the processor. And this seemed to take the advantages of both. So in our implementation, this proved to be the best approach. And here on the right, I've activated the global thread. So here with the darker color, you can see this push and pull strategy from before. And with the lighter color, it's the same strategy, but now on top of it, there is also a periodic global balancing thread. And as you can see, it brings some improvements. Now about multi-level feedback queues, I ran 41 threads at the same time on the same processor. So they'll have to share the processor. Why 41? Well, because we have nice values from -20 to +20, so I wanted to have one thread with each nice value. I recorded how many CPU ticks each thread with the corresponding nice value received. And then I changed the priority computation formula to see how that affects the CPU share. You can see here, those are the results. What we can notice on the y-axis, we have the CPU share. And what we can notice is that for very negative values of nice, we have an almost constant CPU share between them, slightly decreasing, after which we reach a drop-off point where the CPU share drastically increases until a cutoff point at positive values of nice. So this line with blue here, it's this formula left unmodified. And what we noticed is that by changing different coefficients, we could move this drop-off point around. So for example, if we double the coefficient of nice, so instead of 2, we put 4 here, we moved this drop-off point to the right, but we also decreased the maximum CPU share that's attainable. Also, different changes could result in the same output. So for example, by doubling this coefficient of nice, we obtain the same result as when we divided the coefficient of recent CPU by 2. So this is 4 times nice is in here in black, and recent CPU divided by 8, it's in here in yellow, and we can see that those changes result in the same behavior. So some conclusions, we saw that push performs better for lighter loads while pull for heavier loads. And in our implementation, using both provided the best results. And when talking about multi-level feedback queues, we saw that we can control how the CPU time is shared between threads based on their nice value by modifying the coefficients in the priority computation formula. A bit about our future work, what we could do next. So we haven't experimented with the thresholds, so we could check to see which thresholds give the best results. For example, for push or pull, what's the best threshold for those. And also we haven't experimented with the period for the global balancing thread to see again which period would give the best results. We could also improve our algorithms a bit. For example, we could take into account some more complex metrics for load balancing. For example, considering whether the threads are IO bound or CPU bound. So that was my presentation. Thank you very much. If you have any questions.
Okay, thank you, Phil. Questions, please.
Well, we tried to give as much of an overview as we can of how these changes affect the behavior of the system. So someone who has a specific system can look up those results and see, okay, for those values, that's the behavior, maybe that's what I want in my system. But I think that for improving with those complex metrics, we could do something that works on every system and then let someone who wants to adopt those methods change it and adapt it for their own system. Yes.
I also have a very short question. So let's say you decide one CPU has too many threads. You have to remove some of them and give them to other CPUs.
Yes.
How do you decide which CPUs get new threads?
Well, in our implementation, we went pretty simple. So we have we take into account only the number of threads that are on the CPU. So we look for a CPU that has fewer threads than a threshold. So we have a threshold for accepting.
My next question is, what happens if you have 2 or more CPUs with the same number of threads?
Which would try to give, for example.
Yes.
Well, we protect the queues of the CPUs with locks. So only a pair of.
Which one do you choose?
Well, each one, they work in parallel. So each one will try at the same time to pick another one. So it depends on who finds first a CPU that can accept and then take the lock and move the threads.
Mm-hmm. Because I was thinking about introducing an element of randomness. Maybe you consider this for future developments. Could be a good
it's
idea.
not a bad idea.
Okay, thank you. I think
you.
we can move on to the next presentation.
Yeah, hello. I hope the sound is good in the image, but if there is any problem, please notice me here or during the presentation. Okay, my name is Manuel Dragomir, and I'm delighted to present you today the main outcomes of my work on chest X-rays diagnosis using deep learning. But before diving into the subject, I want to share with you the motivation behind it, what made me explore this beautiful and also very important field. As we all know, 2020 was sunk in COVID pandemic, was a medical challenge. The healthcare sector was really suffering. Because the doctors failed to treat patients at the same pace. They failed to set a priority level for patients, and on top of that, the shortage of medical staff and equipment really played an important role. So we focused to find solution to prevent this from happening again in the future, and the main solution is to improve the process of diagnosis, to reduce the error and the uncertainties, make the process more accurate and much faster, using machine learning models. We choose to focus on medical image analysis, very important in the process of diagnosis. More precisely on chest X-rays, a procedure that takes over 2 billion of examination every year. A very important fact to mention here is that a single scan can detect up to 14 serious diseases. We suggest that this is both a very complex problem, but also a very important one. So developing a machine learning model is also very important because it could act as a second opinion. It could even replace a professional diagnosis in the poor villages, for instance, and also it can facilitate the process of learning for doctors in training, having an automated tool. So what were the main problems that can be tackled, and I can tackle in this paper is the binary classification, which is very important, although it is much simpler than a multi-class or a multi-label approach. But its importance comes from the fact that it's increased reliability. The main idea can be seen in this capture. A model can and should take an image and predict healthy or unhealthy, and very important probability of the prediction. Another fact that should be mentioned here is that the binary classification would avoid class imbalance, which appears if you have a class or a disease with very few instances relative to the number of instances in the whole data set. Advancing to another problem tackled was the lesion detector, which is an object detection kind of problem, because as you can see on these slides, it draws bounding boxes on the scans, and also will label the bounding box. It is very important because it is easy to visualize, and the model can be easily confirmed by doctors, and also it is easy to get an interpretation of the results. Before presenting our contribution, we want to underline the fact that we use VNDR chest X-rays, which appeared in December 2020, a new dataset, the newest one, and a very important one because it is manually annotated by radiologists. The previous ones share the same downside, that are labeled by algorithms. So the doctors wrote some reports, and the algorithms labeled the scan. So this is certainly a source of errors. But this is solved by this dataset, although it does have fewer scans. A short view on the related work. It is important to mention that state-of-the-art is always measured in area under the raw curve, and it is between 0.96 and very important 0.98. About lesion detector, mean average precision at a threshold of 0.4 was obtained very recently in April 2021 of 0.37. About our work, we, as far as we know, there is no paper that present an approach on this specific data set. So we chose to use comparative and iterative approach to develop several models and to present comparison between them. To help further research and to reduce time for further research to tune the parameters. This table suggests the best techniques, architecture, data augmentation, optimizers, and the main outcomes that you can see on these slides is state-of-the-art performance, 0.98 area under the curve. Another staggering performance that we consider is achieved with our homemade architecture, which achieves 0.96 area under the curve. This performance, although is slightly worse than the one achieved with Inception, but was achieved with our homemade architecture and trained from scratch in a relatively less time, 2 hours of achieving this area under the curve with from scratch architecture. I think is very useful. Related regarding the object detection, we use YOLO as one of the presenters mentioned before. So YOLO state-of-the-art algorithm for object detection. We did not achieve state-of-the-art like for the binary one, but we achieved good results, 0.32, relatively close to 0.37, but we achieved this result at a threshold of 0.5. So very good results for this one. On this slide, these images were not included in the report, but we use them to get a better interpretation of our results. It presents an unsupervised learning algorithms run on this on the bounding boxes relative to their areas, to their position, and as we can see, the TSNE obtain better clustering. We can see that these two classes, as you can see before, achieve the better mean average precision. It is very important to mention that we have done several useful and important experiments that can help for the research. We've done with several YOLO architecture with several image sizes, and the best one was achieved, as you can see on this slide. As final words, I want to remark that this dataset is very, very important, and it has a lot of potential to build many models, many important models, two-class models, or multi-label or object detection. We achieve very good performance, state-of-the-art for the binary one, and also close to the state-of-the-art for the lesion detector. With low hardware resources that can be improved in the future. We train for only 50 to 100 epochs for 2 to 4 or 5 hours, but this can be further improved with specific techniques. So more data augmentation techniques like gamma noise techniques or Gaussian noise. So yeah, and of the final question that arising here is that would I let myself be diagnosed by these models? And I can only answer with a joking here. Well, yes, but actually no. Yes, because I would definitely take into consideration the results predicted by these models, but human expertise is still indispensable. A doctor opinion should also be taken into account to confirm the diagnostic and to offer further treatment. So yeah, I hope it was interesting and fun. And if there are any questions, I'm eager to answer as many as I can.
Have you talked to some doctors about your results?
Not really. I tried to test my model on chest X-rays obtained from from local hospitals, but I did not manage to get these chest X-rays labeled, so I didn't manage to do that.
Okay, maybe in the future.
Yeah.
Thank you.
Yeah, the real life context is much more difficult because the scans can differ from hospital to hospital. So I think that augmentation is very important to be further investigated, and yeah, different techniques, different approaches for that. So focusing on that augmentation and related for the object detection, also data augmentation, and what I haven't mentioned is that these scans were labeled by 3 radiologists. So each scan was labeled by one radiologist independently. So there can be errors between, or not specifically errors, but some misinformation between the diagnosis offered by the radiologist on the same scan. So maybe investigating how to merge the bounding boxes labeled by the radiologist. Maybe this is a limiting factor, I think. Thank you for the.
Yes, but it's also from your university, I think. So please.
Yes. So I'm going to share my screen and okay. So good afternoon. My name is Tarno Ilya Christian, and today's presentation will be about the problem of EEG seizure event classification that is attempted to be solved using common machine learning and signal processing approaches. First off, I'm going to present some information about EEGs. EEGs being recordings of the electrical activity of the brain and are mostly used in the diagnosis of neurological disorders. One of these disorders is epilepsy. And in order to diagnose epilepsy, neurologists rely on the visual inspection of EEG recordings, which is a time-consuming process that could be automated. An example of an EEG recording that lasts 1 second can be seen in the figure on the right, and that is on 5 different channels. A problem that concerns itself with the automated interpretation of EEG signals is the seizure event classification problem. This problem is based on the Temple University Hospital EEG events corpus, which is a data set that provides labels for 6 different types of classes. 3 of these classes are epileptiform and are of clinical relevance, while the other 3 consists of artifacts or background noise. In the image of the right, there is an example for each type of signal, with the epileptiform ones on the left and the other ones on the right. An important aspect here, however, is the fact that the background class encompasses all signal types that could not be classified as the other 5. In terms of data distribution, we have the following table, which presents each type of event together with the number of time steps, which represent 1 second of an EEG recording. And here we can see that the background class has the most number of time steps, while the SPSW event, or the spike and slow wave event, has only 187. As far as methods go, feature extraction methods that are based on signal processing were used, together with classifiers that were previously used in other EEG classification problems. The processing pipeline can be seen in the diagram. And we firstly extract the signal on the interval of interest. In the pre-processing stage, we resample the signal to have a sampling rate of 250 Hz, after which we pass it to the feature extraction pipeline. This feature extraction pipeline extracts meaningful features, which are passed to the classifier, which outputs one of the 6 events. Next, I'm going to quickly walk over the feature extraction methods and the classifiers which were used. So first off, we have the statistics, which are taken from different representations of the signal. We also used filters like finite impulse response filter or the Butterworth filter. The output of the Butterworth filter can be seen on the right. On the top is the original signal, while on the bottom is the filtered one. Principal component analysis, or PCA, is another common method used all across machine learning and is used to reduce high dimensional data to a low dimensional orthogonal feature space. Next, we have the spectrum, which is a way of representing the signal in terms of its frequency, an example of which can be seen on the right. The correlation method is a method that makes use of the Pearson's R correlation matrix, which is computed in both the time and the frequency domain of the signal, together with the eigenvalues of this matrix. The short time Fourier transform is defined as the Fourier transform which is applied to a segment of the signal that is extracted using a window function. An example of such a window function is the Hamming window, which can be seen on the screen. And this window was used to produce the spectrogram on the right. Another method which uses the Fourier transform is the power spectral density, and this method describes how power is distributed across frequencies. This was estimated using Welch's method, and its representation can be seen on the right. The discrete wavelet transform is used to analyze signals at different time and frequency resolutions by scaling and shifting a wavelet object. And this expresses the signal in terms of wavelet coefficients. In the diagram below, you can see a representation of the DWT algorithm. So first, the signal is passed through a low pass and a high pass filter. This is then downsampled by a factor of 2, from which we obtain the level 1 approximate and detailed subbands. This process is repeated for the approximate subband to get the level 2 coefficients. An example of the DWT decomposition can be seen on the right, where on the top is the original signal and on the bottom are its corresponding components. And the last feature extraction method which was investigated was one based on substral coefficients and differential energy, which is a method specifically designed for these classification problems, but has only been used in conjunction with hidden Markov models so far. In terms of classifier, support vector machine was tested with a multitude of kernels, with the RBF kernel being providing the best results. We also investigated the multi-layer perceptron with 4 hidden layers, which representation you can see in the top right. 3 different types of convolutional neural networks were used as classifier, one being based on 1D convolution, the other on 2D convolution, and the last one applies one-dimensional convolutions to each specific channel of the EEG. The layers of these models are automatically generated based on the input size. And an example of a one-dimensional CNN can be viewed on the bottom right. We also tested a recurrent neural network, which uses 256 GRU cells, which is a pretty standard model. And also a combination of a CNN and an RNN, which uses 1D convolutions and max pooling layers, followed by an RNN with 256 GRU cells, and then we classify the result using a fully connected classifier. Okay. The results vary in terms of classifier and feature extraction methods that were used. So for the SVM, the results are usually above 50% accuracy, with the best method being the correlation method, which had about 60%. The MLP classifier obtained two results which are over 60%, and that is the method based on PSD and the one based on DWT. For the one-dimensional convolutional neural network, this was the most tested classifier, as it could accommodate a wide range of input shapes. And the best method for this classifier was the correlation method, which it also achieved the highest precision out of all the models, and that is 67%. The two-dimensional CNN had the overall worst performance, with most metrics being below 40%. In this case, PCA had the best results, namely 45% accuracy and 51% precision. The MCDCN, or the multi-channel CNN, had the most numbers of parameters, and it was specifically designed to recognize events on different channels. However, this classifier was only able to achieve an accuracy of 48%, and that is using the STFT method with a Bowman window of length 32. The best results for the RNN were with the PSD method. This obtained over 60% for all metrics. The last classifier is the combination of CNN and RNN, which represents an original approach to clinical EEG classifications. And this model had good results for the spectrum and correlation with almost 60%. So in this table, we can see all of the models that were actually able to predict all of the 6 classes. And in the case of GPED and PLED, some of the models obtained better results than the reference papers, which had approximately a precision of 65%. And in our case, we were able to achieve precisions up to 78 and 71%, respectively. This also happened for the eye movement class and the artifact class. However, these are not of such great importance. The main problem of these models were the fact that they were not able to recognize the SPSW event, or the spike and slow wave event, which in contrast to the reference papers, they achieved a precision of 33%. With this in mind, we concluded that the best feature extraction methods were the correlation method and the spectrum method, and for some models, also passing raw signals produced decent results. And the best classifiers were the one-dimensional CNN and the combination of CNN and RNNs. So for further improvements, and in terms of feature extraction, a combination of the previously mentioned methods could be used, as well as features extracted using chaos theory or methods which are based on computer vision. As far as classifiers go, specific classifiers could be developed in order to improve the detection rate of specific events, most notably the SPSW event, as well as spiking neural networks, as they have not been extensively tested in this field. In conclusion, a new approach to solving the event classification problem was presented, and this uses a combination of different classifier and feature extraction methods. However, the problem still remains a difficult one to solve. This is in part due to the fact that the dataset is imbalanced, as well as to the fact that there is a high similarity between some of the signals. In order to achieve a clinical relevance, the clinical relevance threshold of 95% sensitivity and 5% false classification rate, most likely newer methods will have to be developed. This is the end of the presentation. Thank you for your attention.
So I have the same question. Have you consulted with some medical doctor?
I have not, since most often than not, EEG records are kept private. In this case, I have found a really large database which actually has around 30,000 EEG recordings, from which this subset was taken. So yeah, and they are actually real clinical.
I know that
EEGs.
they are reluctant to to share data. This is a bit off topic, but how do you think we can bring or increase the interest of medical doctors in this area?
I mean, I think the interest is already there, although they tend not to trust these automated solutions that are proposed, and that I think is the main problem.
So the solution would be to propose a really, really good automated system that would impress them. No?
Yes, that okay. In the first place.
I look forward to seeing this.
Okay, great. Any other questions? Of course. What I have tried is eliminating the events which did not have a large number of timestamps, in this case SPSW or eye movement, and this actually increased the accuracy by a little bit, but that's all I did. And also another problem which could be considered is the four-way classification problem for this, and this involves taking just the epileptiform signals and one signal type for the background or artifact class.
Thank you. So I think we can move to the next presentation.
Thank you very much.
Mr. George Mihaly, please.
Yes, just
identifying zero-day binary attacks in mainstream applications.
Just a second. Can you hear me?
Yes, we do. Please proceed.
Okay. So my name is Mihaly George, and today I'll be presenting my thesis, identifying zero-day binary attacks in mainstream applications. First of all, let's answer the first two questions that come to mind when hearing the title. The main purpose of binary attacks is to obtain information in an unauthorized way, taking advantage of vulnerabilities at the source code level that leads to a memory corruption in a manner controlled by the attacker. Answering the second question, what is a zero-day attack? It is an attack that exploits a vulnerability that has not been publicly disclosed. So everyone uses applications such as browsers or office software such as Microsoft Word or PowerPoint, but only experienced users are completely aware of the risks of using them. They are heavily targeted by the attackers in phishing attempts or other exploitation techniques in order to steal valuable information. The motivation behind this paper is to find the latest attacks and vulnerabilities and to inform software vendors about them before they are exploited, causing damages. As related works, I want to present the ideas of Tudor Dumitraș and Leila Bilge from their work before we knew it, an empirical study of zero-day attacks in the real world. They implemented a mechanism for identifying zero-day attacks based on data received from 11 million hosts worldwide. They described the timeline of a cyber attack with the key moments within it. The relationship between the time when the vulnerability was discovered by the vendor, TD, it can be seen here in the picture, and the time when the exploit was released in the wild, TE, cannot be determined in most cases. But what we know for sure is that for a zero-day attack, the time when vulnerability was disclosed publicly, T0, is always greater than the time when exploit was used in the wild. Their results consist in identifying 18 vulnerabilities exploited before they were revealed. Within those, only 7 of them were involved in a zero-day attack and had a CVE identifier associated with them. They also found some valuable information regarding zero-day attacks, such as they affect just a small number of users, except for high-profile attacks, and they last about 10 months on average. While this mechanism proved to be efficient in detecting such attacks, it only did so after the attack had already taken place and already caused damages. Now I want to present my proposed method for identification, for zero-day identification. The mechanism uses the result produced by an existing anti-exploit module. It analyzes the detections generated by it, correlates information, and produces a report containing the characteristics of a zero-day attack that were identified in the generated alert. This is the architecture of the entire mechanism, consisting of anti-exploit module and the zero-day identification module. The anti-exploit module has 2 components: a mini filter driver, which registers callbacks to intercept process creations and image loads. The second component is a DLL, which injects into monitor processes and protects them with a series of heuristics. The identification module is a module written in Python, which aggregates data about known vulnerabilities. This data is received from the National Vulnerability Database and uses also information about anti-exploit monitor processes to be able to produce the characteristics of a zero-day identified for a given detection file. It basically works on 3 approaches. The first one, it finds the vulnerabilities associated with the monitor process. So it identifies all vulnerabilities disclosed to the public that affect a specific version of a software application. The second approach, it identifies the affected version of the monitor processes. Basically, it compares the version of the process in which an alert was generated with all versions known to be vulnerable. And the last one, triggering an unusual alert. It is analyzed if the generated alert is atypical to the monitor process. In other words, if it has not been generated within the same process lately. This is the full sequence of operations. So the attacker initiates an exploit on a vulnerable application, for example, Internet Explorer. The iExplore.txt process is created, after which the anti-exploit module initializes the detection mechanisms. Then the malicious code of the attacker is executed, which is intercepted by the DLL of the anti-exploit module and blocked by one of its heuristics. Following the block operation, an alert is generated, respectively a detection file, which is taken over by the zero-day identification mechanism. It aggregates the information regarding the alert generated with the metadata of the monitor processes and with the known vulnerabilities that affect the present process. Thus, a file is produced that summarizes the particularities of a zero-day attack, identified for the recent generated alert. This is an example of a zero-day characteristic file containing the process name in which the alert was generated, the vulnerabilities identified for the process, and the output of the three approaches presented earlier. In order to test the validity and the functionality of the system, the mechanism was tested on over 40,000 detection files from 2020. 60,000 CVEs from National Vulnerability Database were used in the testing process. Now I want to present a case study on 3 popular CVEs along with the result of my mechanism. The first one, CVE 2020-0674, is a use after free vulnerability in the scripting engines of Internet Explorer. To be more precise, the arguments of a comparator function used by sort method of an array are untracked by the garbage collector. This vulnerability was identified in the wild by security researchers from 360 Core Security. The hacker group called Dark Hotel claims these attacks. Their name comes from the way they act. Namely, they track travelers' plans and attacking them via hotel Wi-Fi. The zero-day identification detected that a new version of a monitor process has been identified that is vulnerable, and an unusual alert was generated, which was not encountered in the last period of time. The second one, CVE 2020-1062, is another vulnerability in scripting engines for Internet Explorer. This time in the way that the function JS array push manages memory. The results produced are the same with the previous CVE. A new version of a monitor process has been identified that is vulnerable, and an unusual alert was generated. The last one, CVE 2021-26411, is another use after free vulnerability leading to a double free in MS HTML. The attacks exploiting this vulnerability were conducted by North Korean hackers and targeted security researchers. They operated with fake Twitter accounts that initially retweeted valid security posts, building their reputation. After that, they replaced the links in their posts with malicious ones. The mechanism found that a new version of a monitor process has been identified that is vulnerable, and an unusual alert was generated. So in conclusion, the mechanism developed in this thesis represents an automatic and proactive method for identifying zero-day attacks in the wild. The identification being made very close to the time they occur. As future improvements, I want to improve the telemetry, and by telemetry I mean the data, the information received from the anti-exploit module, and to aggregate information on vulnerabilities from several sources. Thank you for listening to my presentation.
Thank you for the presentation. I have a question. So it's a very challenging, let's say, attempt that
I know.
tackled, but I'm curious, how do you see your approach being used in practice by specialized companies or by individual users?
Yes, my approach could be used by security researchers, because they have all they need to all the data they need to work with, and they can find zero-day vulnerabilities and zero-day attacks very close to the time they occur, so it can be very useful for them.
Okay, thank you. Other questions, please? Okay, so thank you very much. I don't think we have more questions. In addition to our regular program, I think we have another candidate which will present his paper. I believe we are talking about Mr. Kazachuk, or is it Mr. Kazachuk?
Yep.
So it's from Babeș Bolyai, so please, Alina.
Can you see my screen? Okay. Okay, so welcome everyone. I'm Kazachuk Valentin, and I will present you my research about recommendation systems, mainly based on variational autoencoders. So let's talk about first recommendation systems. What is it? Well, if you watch YouTube, for example, when you are watching a video, on the right side, you can see a Watch Next panel that actually represents the recommendations made by YouTube, specialized for you. So these recommendation systems help not only the users to navigate through the vast amount of content that a platform presents, but it also helps the companies to increase their engagement with their user base. And a notable example of this is actually the fourth point of this slide, where Netflix self-reported that 75% of what people are watching are actually because of their recommendation system. Another important point, in my opinion, in the recommendation systems research scene is the Netflix prize contest. So basically, Netflix organized a contest where if a team could beat their system by at least 10% in terms of accuracy, they will receive $1 million. And here in this image, you can see the team Belcore Pragmatic Chaos that actually won the contest. And why I think it's important, it's because it really pushed researchers to improve and come up with new ideas to push the boundaries of recommendation systems even more. So I'm going to talk a little bit about how this is done in practice. So there are three main approaches for this. The first one is content-based, where you recommend items to a user based on his preferences and how similar the items are to his other, let's say, highly rated items. Another approach is the collaborating filtering one, where you take into account the user implicit and explicit feedback, but also how similar the users are, and make recommendation based on that. And the third one is, of course, a hybrid approach where you combine the other two. So we are going to talk mostly about collaborating filtering. So this is mostly done using something called matrix factorization. That is, given our matrix of ratings, for example, each cell represents what rating the user gave to an item, we are going to decompose this into two other latent matrices, one for users and one for items. This is usually done using something called singular value decomposition, but we are going to propose another idea to obtain these latent features. More exactly, we are going to use a variational autoencoder. That is, we input a feature vector, we run it through a function, and we obtain a Gaussian distribution with mean and variance. And by sampling from this distribution and running through another function, we obtain an output that we are trying to make it as close as possible to the input. And why we are doing this is because this value z here that we are sampling from the Gaussian distribution, we are going to use for the feature vectors that we presented here. So let's see the investigated approaches. We will have three approaches. The first one is a more classic matrix decomposition, that it's usually how it's done in practice and how it was done for many years. And the other two are my proposed approaches that I came up with by combining multiple other approaches from the literature. So the first approach, it's not really a classic matrix factorization because it also has a Bayesian component, but it's quite simple. So the rating matrix, we are trying to decompose it into the user features and item features. And each of them are distributed according to a multivariate Gaussian. And each of these parameters are actually distributed to another constant Gaussian Wishart distribution. And this is how it was also, this is another idea that was used in the Netflix contest. So, yeah. The approach that we propose is to first use two variational autoencoders for this. More exactly, we give the network the user features and the item features, and we obtain the latent features. And by multiplying them, we get the predicted rating. The other approach that we propose for this is to take the previous architecture and add one more component. Well, two components. So a component for users and a component for items. And these are actually Bayesian features because they are distributed according to a multivariate Gaussian. And when we are optimizing these features, we'll add them to the features from the previous approach and obtain a more accurate representation of the latent space. So when we will multiply them, we'll obtain an even better, well, we hope it's an even better rating. So the methodology for this. First, we chose 3 data sets. So we have enough data points for this. So the 2 data sets are mostly based on movies, and the third one is based on books. And each of them, as you can see in the third column, they have a non-trivial amount of ratings. The last column actually presents how sparse these matrices are. For example, in the first dataset, only 6.3% of the ratings are actually known. The other are zeros that we are trying to approximate. So yeah, this is why this problem is this hard and really needs an intelligent algorithm for it, because most of the ratings are missing. So to ensure that our approach is statistically significant, we are going to use a 5-fold cross-validation technique, and we are going to average the root mean square error for all the 5 iterations and then present it. So let's see the results. First, we are going to talk about how accurate is it. Well, another important thing to notice is that the first column is something called the item mean. This is not an intelligent approach. This is just taking the mean of an item and reporting it as the rating that each user will give to that item. And this is nothing intelligent about this, but represents a pretty good baseline that we can compare with. Okay, so as you can see in the bold column, the approach based on vanilla matrix factorization with a Bayesian twist actually outperforms all the other methods we proposed. But another interesting thing to notice is that the Bayesian variational autoencoder actually performs significantly better than the approach without this component. Another take on this is how fast the training is. Well, of course, the training for the item mean is almost instantly, but the one for the vanilla matrix factorization, which was also the most accurate, takes the most time. which is understandable because it cannot benefit from GPU acceleration compared to the deep learning approaches. And of course, the method using purely neural networks is the fastest one to train compared to the other one with the Bayesian component that also cannot be accelerated by GPU. Well, it can be accelerated by GPU, but not as much as the deep learning approaches. And another very important take, I would say, is how well does it handle cold start? So basically, cold start is the problem where a new user or item appears in the system. Well, this proves to be very difficult for the vanilla matrix factorization because, as far as I know, it cannot handle this without retraining the whole algorithm. But the second and third approaches perform pretty well on this. That is because the variational autoencoder does not really care about the input. For example, you can, if a user does not appear in the system, you can just pass the variational encoder the movies that it likes, and it will figure out some latent representation. Not as accurate as the other ones that it was trained with, but pretty good. But the third approach on the based on the Bayesian component, it will still need retraining. So yeah, there's advantages and disadvantages. So for conclusions, I would say the main takeaways of this is that recommender systems are necessary for both users and companies to help for a better experience on the platform. Also, the deep learning approaches still struggle to beat vanilla matrix factorization when you are comparing on things like root mean square error. I will also point out that this comparison and the fact that deep learning approaches are not as good is still in line with other research done in this field. There's actually a paper from 2019 that outlines exactly this point. But there are, of course, advantages to the deep learning approaches, such as the lower training time and the fact that it can handle new users or items. And for future work, I outlined here some things that could improve the accuracy, but I'm not really going to go deep into them because I will have to explain the variational autoencoder architecture a bit more so you can understand where they are coming from. Yeah, and that's about it. If you have any questions. Well, yes, so I chose the datasets that I mentioned because the first two actually are the most researched datasets in this field, the ones with the movie lens. Yeah, the first two are the most researched ones, so they have the most papers used on them. So I thought it will be helpful to have other approaches compared on them, so I can get some metrics. And the third one is actually not so commonly used, but I wanted to use not a movie dataset, for example, the Netflix that I mentioned, because I wanted to outline how these methods can be applied to any kind of items, not just movies. Mm-hmm. Yeah, it will really help to use something really different. In my approach is not really important because I'm not using any metadata for the movies. The system doesn't know that it's working with movies or books or anything like that. It just knows that it's items and these are the ratings. But yeah, it will be interesting to use something vastly different from this. Thank you.
Yes. Okay, so we meet again a bit later on the general channel. Yes. Thank you, everyone.
Thank you.